We're talking about thin lenses now. So thin lenses, we're talking eyeglasses, contacts, magnifying glasses, that type of thing. So we have two types of thin lenses, and they're both represented in these pictures below. And the names of these lenses are hopefully fairly straightforward. This left lens is called a converging lens. If we have parallel light rays, all parallel to that optical axis, if you recall, with our mirrors, it's the same, similar with our lenses. The optical axis is the line perpendicular to the surface. And so it experiences no refraction. It doesn't bend because it hits at an angle of 90 degrees, 90 degrees to the surface, so 0 degrees relative to the normal. A converging lens converges those light rays when they refract. A converging lens is also called a convex lens because our object would be on the left side, and this surface here bends out towards the object. And so this is considered a convex lens, similar to our convex mirror, because of the way it bends. The diverging lens is also called a concave lens. A diverging lens, when the light rays refract, they diverge from each other. So similar to a mirror, we would project back, just use dotted lines to project back, and this point up here would be considered a virtual focal point, which means in calculations, we will need to use a negative value for that focal length. Concave lens, because the object would be on the left side, and this surface is curved like a concave mirror, a cave like I can walk into it. So when we talk about lenses and these different types of lenses, these two types, they don't have to be shaped exactly this way. These are the common shapes that we see if we have converging lenses and diverging lenses in the classroom, if I could bring them in for a demonstration. It turns out that the equations that we used for mirrors that related the object distance, image distance, and focal length is valid also for our lenses. Object distance will still be the distance from the object to the lens. We do assume, if I come over to our pictures, we will draw a line that goes through the middle of the lens, and that's true for either lens. And we measure object distances, image distances from those lines, which I'll do some examples so that you can see that situation. The magnification is still negative S prime over S. The absolute value of the magnification is the size of the image over the size of the object. So the nice thing is these basic equations work for our thin lenses in addition to our mirrors. Now, in terms of what determines the focal length of a thin lens is what the lens is made of and the radius of curvature of the two sides of the lens. So I'm going to pull a picture in from our book to show you this. So in terms of what determines the focal length of a lens, now this picture here is a bit, it can be a bit overwhelming with all of the different light rays that are coming and they're drawing. So here is our object, and they are showing us refraction at the two different surfaces. ultimately, what we want to recognize is this equation right here called the lensmaker's equation. 1 over f, where f is the focal length. Now, n is the index of refraction of whatever material the lens is made of. The 1 here assumes the lens is being used in air, so, glasses on our face. R1 and R2 are the radii of curvature. So if our object is on this side, R1 is the radius of curvature of this first side. R2 is the radius of curvature of the second side. So R1 is the radius of curvature of the side closest to the object. And then R2 is that second surface the light will pass through. And we have designations for the signs. R is considered positive if R is convex towards the object. In this picture, R1 is convex towards the object. Just like a convex mirror, it bends out towards the object. R is negative if if that surface is concave, which in this particular case, it is concave, that second surface. Ultimately, our focal lengths are positive for converging lenses. They're negative for diverging lenses. And then our images, it turns out that real images are still going to be a positive S prime value, but they will appear on this opposite side of the lens compared to the object. So we could say the back side of the lens. So that's backwards from the mirrors. Real images for a mirror showed up on the same side of the mirror as the object. So when you look at the table that we have in our test notes, that is why you will see image distance listed separately for lenses and mirrors. And then virtual images will be a negative S prime, and they appear on the same side. So let's talk about these images and show how we can do some ray diagrams to represent where our images will be located. So for a converging lens is thicker in the middle, thinner on the edge. A converging lens is named such because parallel light rays, all parallel to this optical axis, will converge. They refract and converge as they go through the lens. So if light's coming from the left side, they will converge and pass through this focal point on this back side. There is a focal point on the left side as well. If light was coming from the right side, it would focus at that left focal point. So similar to a concave mirror, it is possible, let me finish that. So if you recall a concave mirror, we could put our object outside the radius of curvature, in between the radius of curvature and the focal length, inside the focal length. A concave mirror gave us both real images and inverted images, just depending upon where the object was located. Converging lenses are similar to this. The images we get are real or virtual based off of where the object is located. So my object here, my object distance would be from the object along the optical axis to that midpoint of the lens. I can draw ray diagrams, two light rays to estimate where my image will be located. So if I draw a light ray parallel to the optical axis, and notice I actually didn't even hit the lens, I just go to that middle line. I drew my object taller than the lens, which is fine. This light ray will refract and bend and go through that focal point. I need a second light ray in order to estimate where the image will be located. My second light ray, I'm going to go ahead and go through the focal point on this front side. This is just kind of backwards of what I am doing with the first one. It will refract and go off horizontally. So if I go through the focal point on the front, it refracts horizontal. Where these light rays converge, they really are converging back here. Since they really converge, this is a real image. Meaning if we were solving a problem, we would get a positive value for S prime. These real images are on the opposite side of the lens compared to the object. So our object in this case is on the left side of the lens, the image is on the right side of the lens. This image is smaller than the actual object, and it is inverted. Inverted means if we were calculating a value for magnification, we would come up with a negative sign. Smaller means the absolute value of the magnification is less than 1. So we'll be referring to the table in the test notes that we were referring to when we looked at mirrors to make sense of our answers. Now, one other thing is if you are looking through a converging lens at this object, you would actually be over here. That's a terrible picture. But anyway, you would be looking through the lens where the object was on the opposite side of the lens from you, if you were looking through it. The image that you would see, though, because this is a real image, you could set up a screen at that location and see the image on the screen. If we take the same lens but we put the object closer to the focal point, if I bring it in nice and close to the focal point, let me draw my other reference line. Here, if I draw the line parallel to the optical axis, I just need to go to the line that represents the middle of the lens. This will refract and go through that focal point. Now, by the way, I forgot to label S prime in my picture above, so let's go ahead and do that really quick. S prime would be measured from this same reference line to the image. Okay, so the second lens down here, if I go through the focal point till I get to this reference line, and then horizontal, these light rays, pretend that bottom one was horizontal, sorry. I don't draw straight lines, obviously, very well. This image, because these light rays really do converge, this is a real image as well. Meaning we would get a S prime value that was positive. This image is bigger than the object, bigger than the object. meaning the absolute value of the magnification would be bigger than 1. This image is inverted, meaning the magnification would be negative if we were calculating values for it. In terms of distances, object distance is from this reference line, the middle of the lens, over to the object. Image distance is from the same reference line over to where the image is located. Real images for lenses. Real images created by lenses are inverted. They are found on the opposite side of the lens compared to the object. This example is the type of lens we have with a projector in a classroom. We project images on a screen. That means they are real. Only real images can be projected onto a screen. So if we're in a classroom and projecting an image onto a screen, we know we have a real image. Which, interestingly, if we want our picture on the screen to be upright, we have to invert the object. You don't get the pleasure of playing with slide projectors. When I was young, that's how we would project our images on a screen, a slide projector. And you had to put the slide in upside down and backwards in order to get the image on the screen to be right side up, which was always a bit of a mind-boggler when I was little. Okay, one other option with our converging lens is to have our object closer to the lens than the focal point. So if my object's in here, draw my reference line again in the middle. I can draw the line parallel to the optical axis, and I know it will refract and go through the focal length. Now this second one, the focal length's behind it, so I'm actually going to take it and draw along the line that would come from the focal length, and this will refract off parallel to the optical axis. These light rays diverge. Similar to what we did with mirrors, if they diverge, we need to dot them backwards to find out where they appear to converge. So here is where they appear to converge. So here is our image. But again, this is a virtual image simply because the light rays don't really converge there. We had to dot them back. That just means we can't see this image on a screen, which is fine. If we're looking through this lens, this is a magnifying lens or magnifying glass. Looking through this lens, we see an image now that is virtual, but we don't care if it's virtual or real. It is now bigger than the actual object. We were magnifying the picture, making it bigger. It is also farther away and upright. So S is the distance from the object to the lens. S prime is the distance from the image to the lens. S prime mathematically would end up being negative, meaning virtual. With a lens, virtual images are located on the same side of the lens as the object. Bigger means the absolute value of the magnification would be greater than 1. Upright means we would come up with a positive value for the magnification. So the converging lens, in terms of the types of images it creates, is similar to a concave mirror. We can get real images or virtual images just depending upon where the object is located. Diverging lenses are similar to the convex mirror in that we only get one type of image. We're going to draw our diverging lenses as thinner in the middle, which is what they are. The parallel light rays diverge as they pass through, meaning we end up with a virtual focal point on the front. So in the picture I showed earlier in this video, the optical axis goes straight through. Here they will refract, this will refract. And so that's where we would dot these back to this virtual focal point. There would be, similarly, if light was coming from the other direction, light from a virtual focal point on that other side. These light rays can be a little interesting to draw. If this is my object, if I draw the light ray that is parallel to the optical axis over to this line representing the middle of our lens, I know it will refract such that if I dot it backwards, it will go through this front focal point. Okay, I need a second light ray. If you recall, in converging lenses up here, my second light ray, I was headed towards the other focal point on either one. So I went through this front focal point and then it refracted off horizontally. The analogous light ray here is to head towards this right side focal point. So if I start drawing my light ray headed towards that point, then it will refract off parallel to the optical axis. These light rays diverge. All that means is we just draw these little dotted lines back, and where they appear to converge right here is our image. Because we have to dot those lines back, that means we have a virtual image. S prime would be negative if we were calculating it. This image appears on the same side of the lens as the object. This image is smaller than the actual object, meaning the absolute value of the magnification would be less than 1. It is also upright or not inverted, meaning our magnification would be positive. Diverging lenses are used for those of us, myself included, that are nearsighted. Nearsighted means I see up close fine. I can read without glasses. I can see up close to me without glasses. But I need glasses to see clearly far away. So if I'm driving and I want to read a street sign, I need glasses to be able to read them without being super close to the street sign. What these glasses are doing, so the glasses are in front of your face. So essentially your eyeballs right here. I'm looking through the glasses and this object is too far away for me to see clearly. The glasses create an image closer to me that I can see clearly. And it is smaller, but the fact that it's closer is what I need. And so with my glasses, I can read those street signs just fine, whereas it's a bit harder to do without my glasses. I have to be closer to the street signs. A converging lens, magnifying glass, these are also reading glasses. So if I scroll up here, the objects, if we need reading glasses, that means we can't hold a book at a normal, comfortable length and read the words clearly. We need to hold it farther away, which, as we get older, it's very common to need reading glasses. So the reading glasses, again, your eyeball would be right up here. It's creating a virtual image that's farther away, where you can read it clearly. It also magnifies it, which helps. So glasses, contacts, this sort of thing. Of course, they make bifocals where part reading glasses and part helping me see far away. All right, so we're going to be looking at some sample problems on how to solve these types of problems. I will link out to some demo videos as well, so you can see these images and what they would look like.